Hey guys, I'm gonna do this first problem here is gonna be for this first video here is gonna be both for both problems 1 and 2. You can see both deal with triangular load cases, and like the concept of triangular load cases seems to have messed up with a lot of you guys on the last homework, and I want to make sure you guys really understand what is going on. So this is the first case. And here is the second case. I'm going to do a very simple example, but I will go all the way through. Keep in mind that the example I'm about to do cannot be just translated directly onto your frame. You have other forces that are going on in your frame, and you need to take those into account as well. So, the problem I'm going to do for you guys right now is this problem. Simply supported beam with a uniformly distributed load. I'm going to call this, it's a function of x, because as you go from, this is L, and as you increase x, the value of your distributed load changes. And I keep messing up when I say that the maximum load is capital W. So instead of calling it capital W, I'm going to call it P. Professor uses W here, but when I write, I have a hard time distinguishing my omegas from my W's. So I'm just going to leave it as P for now, even though P is normally used for a point load. When you're doing this, so where do you begin? Remember that when you have a uniformly distributed load, you always start by, for finding the reactions, you always start by finding the total load. And the total load is always omega times L. And you say, well, let's put this total load in the middle here. But what are you actually doing? You're finding the area of this, turning it into a point, and putting that point at the center of area. The center of area is, for a rectangle, it's halfway. For a distributed load, for uniformly distributed load, where there is no slope, the slope is 0. Your total area is just omega times L. We do the same thing for triangular load. What is the total load here? The total load is just the area of a triangle. It's P times L over 2. Where does it act? It acts at 1/3 from the base. So this becomes this. 1/3 L. So when you're finding your reactions, you need to take this into account. So let's call this A, we'll call this B. So your moment, okay. The reason why this being off center is important is because when you're finding your moment is based on these two arms. So if we take the moment about A to get reaction of By, let's take clockwise being positive. So you have PL over 2 times 2L over 3, right? Because that's this length. 2L over 3 plus 1/3 L equals L, which is the total length, minus BYL equals 0. So By equals PL over 3. When you do the summation of forces, it's not PL minus PL over 3, it's PL over 2 minus PL over 3 minus AY equals 0. AY equals PL over 6. And this makes sense, right? Like, because most of the load is concentrated over here, the reaction force at B should be higher than the reaction force at A. Now that we have this taken care of, let's find our moment, our shear. So let me switch pencils here. Let's do, let's take a cut. You always want, when you take your cut, you always want to start at the vertex. Because if you start at the base, let me draw that over here. If you start at the base, you have to find the area of a trapezoid, which is not that hard, but you also have to find the center of mass of a trapezoid, the center of area of a trapezoid, which is very tedious, and it's not something you want to do if you can avoid it. So I start from this end. I say that this is x. I have as my load, and I have some force v. Well, what is the height of this triangle? We don't know right away, right? We have to calculate this. So, do you agree that this is a line? And if this is a line, I can express the height of this triangle as a function. I can express it as a function of x. So y equals mx plus b. And then what is the value at x equals 0? It's just 0, right? What is the slope? The slope is just the rise over the run. So my function of x is equal to p over L times x. So when I come over here and I'm trying to find my shear, what is my shear? I have PL over 6 minus V minus the height at this point minus the height at the cut, PLX, times the distance, the length of the cut from here to here, the distance to the cut, times x, times 1/2, right? So my V, if I equals 0, so my V equals PL over 6 minus PX squared over 2L. And this becomes my shear equation. Note that my shear has a power x to the power of 2. And this is why I was forced to deduct half a point from many people on problem 3 of the homework of tutorial 3, because your shear was a function, the highest power in your shear was x. And that is not the case. You have an extra x term in here because your omega is a function of x. And that is something that you have to keep in mind. If we look at our moment now, our moment equation is going to be pretty similar, right? I do, let's take m counterclockwise. So m plus, now I just need the total load. Do you agree that this is the total, this is total load? So if I take the total load, and I need to multiply it by the distance. Well, what's the distance? The distance from the cut to the point that I'm interested in is just, x over 3, right? So over here, the distance to my cut is x divided by 3. And then my reaction is PL over 6 times x. So what is my moment? I want to keep this on one page here, so I'm just going to squeeze it in at the bottom. No, I'll squeeze it in over here. PLX over 6 minus PX cubed over 6. And again, we went up by 1 power. So it went from a square to a cubic. You're always going to go up in power as you go up in forms. And what's the only way I can think of showing this to you is if you remember your equations, your v equals the integral of omega x, approximately. Your m equals the integral of your v. This is your slope, if you remember you're working with slope before, is like this. And your so as you go up, as you go down, I guess, you always add an extra power. So this was a function, in our case, a triangular load. It changes as a function of x linearly. So it's x as a function of x. Your shear becomes a function of x squared. Your moment becomes a function of x cubed. Your theta becomes a function of x to the 4th. And your delta becomes a function of x to the 5th. But anyway, yes, these are the equations that you're going to get something that's similar to this. You should get these powers. As a matter of fact, you must get these powers. That was one of the things that I'm looking for when I'm grading this. You need to see, the easiest way for me to check to see if you actually understand this is if you get the right powers. And about half of you did not get the right powers. You got x squared. So you got this as a function of x, and this is a function of x squared, which is not correct. Keep in mind that this is not the same thing that you have in your problems. Your problems, you'll have an extra moment in shear term because of this pin, because of this extra arm here. I did not do a problem with this arm, but I believe that now that you actually know how to do a triangular load, and because you already did entire homework on frames, that I don't need to go into too much detail on that. But yes, let us know if you have any questions about this. I think that this x over 3 term and the distributed moment is what's causing a lot of issues. Oh yes, before I forget, this is not 2x over 3. This is the distance to your cut. The distance, you're always making your cut, you're measuring your moments from the base, and the distance from the base is x over 3. There were some people who did 2x over 3, and I didn't deduct points from that, but it's important that you keep that in mind. Anyway, let us know if you have any questions.